Hello and welcome back. I hope you enjoyed yesterday's video, the introduction, just showing you a little bit of my personality. I hope you feel like you know me better. I really enjoy getting to watch all of your videos. Some of them were quite entertaining, but I enjoyed being able to see you and introduce yourself, and I feel like I know you better now. And that makes my job a lot easier when I'm teaching you guys online, because now whenever I see your name, I'll remember part of the video or something that we have in common. So thank you for doing that. Another thing I just want to address before we get started with today's topic is that you guys are all in honors geometry, and some of you chose to be in honors, which is great. Some of you didn't, and you might have been kind of surprised that you were placed in honors geometry. Well, if you didn't choose me, I actually chose you. So I talked to your Algebra 1 teacher from last year. You were either recommended or based on your class rank and your performance in math last year in algebra. We took our top students, we placed them in honors. So all of you guys, you're the best of the best, and I think you guys deserve to have the best math experience as well. And so hopefully you'll be able to see some of that today when I introduce you to the subject of geometry. Another thing I wanted to bring up is you might not necessarily like algebra from last year. Some of you guys even said you didn't like math. Well, to be honest, I'm not really a big fan of algebra either. Of all the topics in math, algebra is probably one of my weakest, and that's probably because I'm not interested in repeated processes over and over again. That is algebra. I know it's kind of mean to say, and it's very important, but still, I think you'll find geometry to be a different math class. And hopefully, if you're very visual like I am, you're going to really dig this course. And so let me give you guys an overview of the history of geometry, which is really the oldest math subject that we have. It's a really rich history. I think you guys are going to enjoy it. If the video is going too slow for you, you can always change the playback speed to speed it up. If it's too fast, you can always slow it down. Whenever you're going through this today, I know there's like cobwebs in our brains, and some of you guys haven't done math in like over 4 months. So this is going to be a lot that I'm throwing at you pretty quick. So don't worry about that. I'm just kind of whetting your appetite to show you the cool stuff that we're going to be getting into this year, and even some really high level things. So I'm challenging you. I know you guys are going to do great. Don't freak out. If you don't understand everything I'm showing you, I'm really just showing off instead of actually teaching it to you per se. So we're going to go through all this stuff a lot slower throughout the whole course of the year. So without any further ado, let's get started. So geometry, as I said, is the earliest form of math that we've ever had. So some of the earliest mathematics was as simple as counting. So here we have two bones that were found in Central Africa. They estimate about 20,000 years ago. So this is prehistory, like before we really knew a lot. So it's like really early man type stuff, and you can see the notches that were being counted in these bones. I don't know what they were recording, if they were counting probably like counting sheep or something, trying to go to bed. Not that type of counting sheep, but this was an early form that shows us that they had an idea of a number system and quantity, and the importance of keeping track of something. So and it wouldn't have been necessarily really easy to carve notches in bone, and since it was so hard, it's clearly preserved over all that time. So after really basic primitive math of counting, the next that really developed, which is where kind of you think of geometry, is calculating area. The reason they needed to calculate area in domestic situations here was for taxes. So they needed to know how much farmland you had, and the bigger your farm, the more taxes that you would be charged to the pharaoh or whatever. A lot of this was going on in Egypt, by the way. We'll actually spend a whole day talking about this topic and an area and how it related to taxes. And I think you'll enjoy that. It'll be a topic for another day, but it was really important along the Nile because it flooded all the time. Then we get into the Hellenistic era. So we've got a lot of the Greek mathematicians kind of after Egypt. This is kind of when they took over. So this is Thales of Miletus. You can see when he was born. I won't read that to you because I know you can read. But he was known as a philosopher. He was the first person to successfully predict a solar eclipse. He came up with the Thales theorem, which is a method for constructing right triangles, which I'll show you on the next slide, and similar triangles and properties of similar triangles, which we will also get into. So let me show you a little bit about similar triangles real quick, just to show you kind of what's going on here. There we go. So if we look, and there's kind of a solution here, but if we have a puddle that's between us and a flagpole, and if we back up away from the puddle so that we can see the top of the flagpole in the center of the puddle, and we measure the height to our eyes and the distance from directly below our eyes to the center of the puddle, and from the puddle to the end of the pole, we can actually indirectly measure and find out the height of the flagpole. The reason this works is because these two triangles are similar to each other, meaning that one of them, this triangle on the right, is just a scaled down, shrunken version of the triangle on the left, which means all their sides are going to be proportional, and by the way, all the angles are going to be congruent. We'll get into all that. I know those are vocab words that you don't know what I'm talking about yet, but don't worry, I'm just kind of showing you the power of geometry and what we're gonna get into. So what we can do is set up a proportion, just like whenever we're looking at, I don't know if it's an analogy, like A goes to B just as C goes to D. The same kind of thing happens. I know that was like an English term, but with setting up proportions. So we have the height of the man to his eyes, 5.5, goes to the height of the flagpole, which is the question mark. Just as the distance between the puddle and the man, which is 6.5, is going to go to the distance between the puddle and the bottom of the pole, which is 26. We would solve that proportion by cross multiplying. So we do 5.5 times 26 divided by 6.5, which would give us an answer of, I believe it's 22. Yeah, 22. So the height of the flagpole would be 22. I think our units were feet in that case. So that is similar triangles, indirect measurement. We're actually going to go outside at the end of the year if we get to, I was going to do it last year, but then COVID hit. But we'll go outside at the end of the year. We'll play volleyball. We'll spend an entire week doing indirect measurement, where we will we'll do these things and many different methods and cool stuff. I think you're going to like it. So another one is Thales theorem. So this is going to look like black magic. But if, say, I have this segment here, and the first thing I want to do is find the midpoint of that segment. Let's see if I can go from here. So what I want to do to find the midpoint is I'm going to use this tool called a compass. Now a compass just takes a set distance. So this set distance here, I'm going to do the same set distance here without adjusting the compass. And when I do that, I'm going to get this interesting shape here. By the way, we're going to use compasses whenever we get back in person. Then the only thing I have left to do is to connect those two dots. Whenever I connect those dots, what that did is it actually constructed a rhombus, believe it or not, and we have perpendicular diagonals from that rhombus, which means this line is perpendicular to that one, forming a right angle, in case you weren't familiar. And it also bisects the other diagonal, meaning this length is the exact same length as that length. But what's interesting about that is that now allowed us to find something we call the midpoint. So this point here is the middle point between the two segments. And so if I extend my compass to this new setting, you'll notice this setting here is exactly the same as the setting on the other side. Why that's important is that means that we found the center of the diameter, which would allow us to construct the circle. If you notice, those go through those 2 points. So let me clean up my construction just a little bit. In case you're wondering, we are going to do these constructions quite a lot, and it's fascinating what we can do with straight edges and compass. I'm just not sure we can do that on an iPad very easily, so that's probably one of those things we're just gonna have to wait till we get back in person. But trust me, once we get through the dam and the fog and stuff like that, we're gonna have some really good memories that I'm gonna make sure you guys get to. So what's interesting, once we have that semicircle, is that now this if we connect any point that's on the semicircle, like this one, to the other two endpoints of the diameter, we have a triangle. And in fact, this is a special kind of triangle. It's a right triangle because this angle here is a right angle. In fact, if we picked any other point on that semicircle, this is Thales theorem, by the way, it's also going to have to be a right triangle. Same thing if we picked any other point. And in fact, on a, oops, that one needs to go a little bit higher. On a semicircle, there's infinitely many points that we could have picked. And all of those points, if we connected it to the opposite two sides of this diameter, we'd always have a right triangle with the exact same hypotenuse length, which is the diameter of our semicircle. That is Thales theorem, and it is pretty stinking cool. Another thing we got from Thales was the intercept theorem. This is another form of indirect measurement. So let's say that we have three objects, A, B, and C, or A prime, B prime, C prime, and the rays of the sun are all shining down on those 3 points at the exact same time. Well, the rays of the sun that hit the earth are all going to be traveling in the same angle. And so, oops, didn't mean to do that. It means I should have locked that in place. Control K, boom, got it. All right, so all those rays are going to hit the top at the exact same angle. forming three similar triangles. You see the small one, the medium one, and the big one. There you go, Goldilocks. That's it. All right, so now that we have those three triangles, it splits the sides in proportions. So this is called the Thales intercept theorem or the side splitting theorem, which means there's some proportions that we can do. So if we know, let me see, I think it's 2. Yeah, 2. So if this side here is 2 and this side here is also 2, then what do you think this side is going to be? So 2 goes to 2 just as 1 goes to not 1. That's clearly going to be longer than this side. So what's really happening? Well, in our small triangle, we have 2 and 1. So this side is half the length of that side. Then in our medium-sized triangle, we have 2 plus 2, which is 4. So this side is half of 4, which is going to be 2. We could also set up proportions down here to get the same thing. Let's say the other side here was 3 because it looks a little longer. So we have 2 goes to 1 just as 2 plus 2 plus 3, which is 7. 7 goes to, I don't know. So if we want to set a proportion to solve for that, we have 2 goes to 1 just as 7 goes to x. Then to be able to solve for the value of x, which is this length here, we just cross multiply. So 7 divided by 2, which is going to be 3.5. I should have been able to do that in my head. Hey, there we go. So pretty stinking cool. Again, we're going to do this outside. Then we have Pythagoras of Samos. Samos is a small Greek island, which is where he was from. This dude's got a crazy back history. He actually had like a super top secret cult, math cult. It's like a religion to them. It was really bizarre, and he made people take a vow of silence for an entire year before he would let them into his math cult, and then he would share all of his secrets of math. Like this guy was crazy, like Illuminati confirmed type stuff. So anyway, Pythagoras was super weird but really cool, and you know him from the Pythagorean theorem, of course, which we're going to go over. And then the most important mathematician of all time is, in my opinion, Euclid of Alexandria. He was also known as the father of geometry, and he wrote a book called Euclid's Elements. Now, this book was the best-selling, or second best-selling book. Not best-selling, this isn't like Amazon or anything like that, but whenever the Gutenberg press was invented in like 1450 or whatever it was, don't fact check me on that one, but whenever that was invented, this book was the second most printed book behind only one other book. Can you guess what that book was? The Holy Bible. Right. So a math textbook, which was written back in, I think, around 300 BC, which is when it was first written, was reproduced many times over again, and was pretty much the only math textbook that people would use, or the most popular math textbook that people would use, and mainly wealthy people who could afford to buy the book would read it and would study math. So if you were an intellectual at all, or if you were wealthy and you could afford to study, then you would have a copy of Euclid's Elements, which was a math textbook about geometry, and that would set you apart from everyone else and make you really smart. So geometry was the oldest math subject, and the book Euclid's Elements, which of course was originally written in Greek, was a very popular book and is still popular to this day. Not the second most selling book anymore. Now we've got other books, but still a really influential book for all of mankind. And you are going to get to study that book, not that book particularly, but that subject of geometry, at least Euclidean geometry. So let's look at the word geometry. So there are two words apart here. So we have our prefix geo, and then the last part, metry. So geo, if you think of geo, what do you think of? I think of a Geo Metro, which is a really slow car, but you're probably thinking of something else, which is the Earth, right? So geography, geology, it's a study of the Earth, okay? And then metry, what does that remind you of? Is there a word that looks like metry? So you're probably thinking metric, right? Or the metric system, which is a system of measurement. So metry is actually root word for measure, or to measure, or the measure of. So geometry, simply put, is the study of math where we are interested in different ways to measure and quantify the Earth and different things that appear in the Earth, namely different shapes. So rhombuses, kites, parallelograms, circles, three-dimensional shapes and stuff like that. How do we measure those shapes that appear in the Earth? I actually kind of forgot what was over here. What is over here? I have no idea. The suspense is killing me. What is this? Are these just dots? Oh, no, those are not just dots. Okay, cool. So obviously that slide did not get locked in place, right? So just scratch that, like that never happened. This is very raw. All right, so if we're talking about studying the different measurements of the Earth, let's talk about taxes. So for instance, let's say that there are 2 plots of land that you're going to buy, right, to raise crops. One of them is a square mile, meaning it's 1 mile by 1 mile. See, it's a square mile. See how that works, right? The other one is a rhombus mile, which means the dimensions of the sides are 1 mile, 1 mile, 1 mile, and 1 mile, just like the square mile, but this is a rhombus mile. The question I would have for you is which one of those two has the most area? Which one is the biggest plot of land? Which one should you charge more taxes? A square mile or a rhombus mile, which is not really a thing. Well, you can probably just visually tell that the square mile is larger than the rhombus mile, and that's true, but can we prove it, and why is that? And if you can see that, you're actually already picking up on something that many Egyptians a long time ago didn't really know, and they were taken advantage of because of it. And we'll go into that historical story a few days later, probably about in a week, but we'll go through it. It's going to be a lot of fun. Okay, then a next question I would have, so instead of a square mile or a rhombus mile, what if we had a circle? So a plot of land that was actually a circle, and it had a radius of 1 mile. Now this is obviously not drawn to scale. If it was, it would be clearly bigger, but I'm trying to trick you here. Which one of those would be the biggest? A square mile, or we've already crossed that one out, a square mile, or a circle with a radius of 1 mile? So you're probably thinking, I think I remember a formula for the area of a circle that has to do with the radius, and is it the 2 pi r or is it pi r squared? Which one of those is circumference, which one is area? Well, the squared one is the one referring to the area, so it is pi r squared. And in this case, our radius is 1, so 1 squared is 1. 1 times pi is just pi. And remember, pi is an irrational number, which is approximated by 21/7, or in other words, 3.141592. 6 something, I don't know. That's about as far as I go. So here we have 1 square mile, and this one, if it was actually drawn to scale, if I actually blew it up like it's supposed to be, would be closer to, oh, check that out. It would actually be 3.14 or pi square miles. So you could actually see if that was drawn to scale like it should be here, it would be much larger. But how do we find those formulas? Where did they come from? And how do we use them in order to determine the area of plots of land? That's stuff we're going to get into. All right, so that was pretty much the basics of geometry. Now we're going to get into the book itself. So Euclid's Elements, the way that he organized it, the first thing he talked about was something called undefined terms. Now, this is probably going to blow your mind. It's going to sound super philosophical and abstract, but it's pretty cool, and I think you can get it. So I'm going to share it with you anyway. Oh, by the way, this is something they taught me in college, but I didn't tell you that because you can totally get it. So just follow along. So let's say we want to start out with some vocab words like blue. What is blue? Well, we all know what blue is, like this right here. That's blue, right? The sky is blue. Okay, so we know what blue is. Some of you are like, my favorite color is blue, right? Okay, gotcha. So we know blue. But let's say we wanted to know, what is the definition of blue? How do we define what blue is? Well, instead of just pointing to something saying blue, look, that's blue, we have to use other words and other terms to define blue. So when we look at the definition of blue, so pick this up from Webster or whatever I did, it says it's a color of intermediate between green and violet, as of the sky or the sea or a sunny day. So notice in the definition, they're also giving examples, but they also use other vocabulary words like green and violet. So it's a intermediate color between green and violet, like, and used in a sentence, the clear blue sky, which we all know what that is. So if you notice, in order to understand what blue is, we have to know this other word, which is green. Green is used in the definition of blue. So these two are tied together. But now we still want to know what blue is, so we look up blue. Blue tells us that it's related to green, so then we look up the definition of green. You see what's happening here? All right, well, green is the color between blue and yellow. So now involved trying to know what blue is, we had to look up green, and now that we know what green is, we have to look up green, and it tells us that it is between blue and yellow. You see the problem here? In order to know what green is, we have to know what yellow is, or blue. And Now I'm just saying colors and I'm all confused. But let me visualize what's going on. This is a vicious cycle of circular logic. So in order to know blue, we have to know green. But to know green, we have to know blue. We're right back where we started. We've got a problem. Like, we got a serious problem. And this is a problem with all axiomatic systems. We have to start out with some basic undefined terms that I can't define what it is, but I can tell you how it interacts with other things. Isn't that kind of cool? All right, but in order to know what green is, we have to know blue, and we also have to know yellow. So we're not even done. It's tying into something else. And then we end up with a bunch of circular logic and issues. Okay, so there are 3 undefined terms of geometry. They are points, which is no dimension, lines, which has 1 dimension, and planes, which has 2 dimensions, like a flat plane or flat surface that extends forever. Okay, we're going to go into more detail on those Monday when we go over all of our vocab, but those are our 3 undefined terms. The basic idea that we're trying to get across here is that we can't pin down and give a definition of what those are, even though I'll attempt to on Monday. We can just describe how they interact with each other, but we can't necessarily define it. For instance, with blue, we just simply have to agree that this is blue. And if you agree that that's blue, we're good and we can move on. And some of you are like, yes, please move on. This is so abstract and weird. It's okay. I promise you the whole class won't be like this. I'm just giving you a treat and really showing you what geometry is all about today. All right, so in our axiomatic system, we start out with things called axioms, which are things that we cannot prove, kind of like undefined terms. You just have to agree with me that blue is blue, and then we can move on. So let's say that we have our 3 axioms, which are yellow, blue, and red. Now, if we all agree this is yellow, we're good, right? Do you agree this is blue? I'm talking to myself, but normally if we were in class, you would say, yes, that's blue. Is this red? Yes, and if you're colorblind, just trust me, that is yellow, that is blue, that's red. Now, if you agree that those are what I said they were, then from that, we have other colors that follow. So if this is yellow and this is blue, now we can define what happens when we mix those 2 colors, which would give us my favorite color, which is green. All right, which I think I'm wearing like green shorts and green shirt today. It's my favorite color. I do that often. All right, then if we combine blue and red, we get another color, purple, right? Yeah, so we get purple. And then now that we have green, we can combine that with red, which will give us, I think, brown. And then that's it. Yeah, and eventually we could get all of our colors from those 3 colors, which is pretty cool. So all I had to have is for you to agree that yellow is yellow, blue is blue, and red is red. And once you agree with those, we can mix them and define the rest of the colors follow from them. And this is an axiomatic system. So geometry is the exact same way. Before I get into geometry, I'm going to give you an example from theology, because I really enjoy theology, and I think theology is as consistent as mathematics. Like, it actually goes together. So the study of theology and the study of mathematics, even historically, a lot of theologians and clergy members were also mathematicians. So you'll find that in history as well, which I find fascinating. So here are 3 axioms, how I would define the 3 axioms of theology. So these are things that I can't prove to you. Isn't that interesting, right? I can't prove to you that blue is blue, yellow is yellow, and red is red. But if you agree with me that 1, God exists, and that 2, the Bible is God's word, and 3, really important, that it's inerrant. If you agree with those 3 assumptions, okay, again, I can't prove it to you, but if you agree that they are true, then from all of that, we get all of our theology, which is our propositions. So by combining that, we get all of our propositions. So everything we believe in, all of our doctrine, our theology, follows from those 3 basic assumptions. All right, another example, which is from like a printer. So let's say that we have 3 colors, yellow, cyan, magenta. So those are the 3 colors that are in a colored printer. So if you agree with these 3 colors, and again, we can't prove that yellow is yellow or cyan is cyan or magenta is magenta. You just have to agree. If you agree with me, then from those combinations, we can get all the different colors in the rainbow, which is like the rest of all the propositions. So what are the axioms for geometry? I'm not going to read these to you because we're actually going to investigate each one of them in a little bit. But these are the 5 axioms of geometry. The 5th one is really important. It's the parallel postulate. So if you agree that these 5 things are true, and you know what our undefined terms are, points, lines, and planes, from that, the entire book of Euclids Elements and all of geometry, everything we know essentially about geometry and measurement and earth and stuff like that, it all follows from these 5 statements, which we cannot prove are true. You simply have to assume or agree with me that they're true. It's kind of cool. All right, so our first, just kind of a description, visual what's going on. So here are our 5 axioms, okay? And if we combine axiom 1 and axiom 2, we might get something like the segment addition postulate, which we'll talk about in a later week, but it basically tells us that we can add segments together. Then, now that we have our segment addition postulate, if we take that with the parallel postulate, that will allow us to create the Pythagorean theorem, which follows from that, or something similar, okay? It's just a simplification, okay? So all of geometry essentially follows from the 5 axioms and the 3 undefined terms. So what are those postulates real quick? We'll go through them just for fun. The first one, which is an assumption, is that we can draw a straight line between any 2 points. So point A and point B, there exists between those two a straight line. Now we would actually draw that straight line by using a ruler. So this is just a construction. So from A to B, we draw a straight line, just like I did here, and we're good to go, okay? So that is an assumption. We have to assume that you are capable of drawing a straight line between any 2 points. All right, the second one is any line segment can be extended forever or indefinitely. Same thing. So if I can draw a straight line in between the 2 points, can I also draw a line that keeps going and extends beyond the 2 points in either one of those 2 directions? Well, you bet we can. So that actually is our second axiom, which is pretty simple. And these are what all of math is built on? Yeah, you're exactly right. All right, given a segment, a circle can be constructed or drawn by using the endpoint as a center. So say we have a segment here, we can draw a circle. Actually need to flip that so it'll look better. Yeah, we'll do it from here, where B is the center, and we can draw a circle going all the way around. So this segment is, axiom is just simply that we can construct circles. And then all right angles are congruent. This is the fourth one. That's kind of sounds trivial, but essentially what we're saying is that if we have these 2 right triangles, this right angle is the same as this right angle, meaning that essentially it tells us that it's a property of superposition, which is that properties and shapes don't change by their location. So a right angle over here is the same as a right angle over here, meaning as I move something through time and space, it does not change its properties, such as its size or the angle. Okay, so I know that was kind of totally trippy and weird, and you're probably thinking, why do we need to assume that that's true, that things are consistent and that as we move them through time and space, they don't change? But it is really important. So that's the fourth postulate. Kind of crazy, I know, right? Weird. All right, and then the last one is the parallel postulate. So this tells us if we have a line and a point that's not on that line, then there exists a unique point or a unique line that goes through that line that will never intersect the other line, and that is a parallel line. So that was kind of cool that they actually did that. So what that's saying is that it's only possible to draw one line, as long as it's on the same plane, that never intersects the other line and goes through this point. So if we try drawing another one that goes through point C, okay, and it's not the same as the original line, then it's eventually either going to intersect the line on the right side or on the left side. And if it doesn't intersect, so let's say that it actually doesn't intersect, well, you know what, I'll just drop it down here. And if it doesn't intersect and it goes through that point and it doesn't intersect with the line on the bottom, then that tells us that those lines are actually the exact same line. So they're not unique, in other words. So this is the parallel postulate. A lot of controversy that goes behind this. I won't get into it, but if you study in college, it's actually really, really cool because it doesn't follow from the other 4. And they spent thousands of years trying to prove that you didn't need this postulate, but you actually do. Okay, spoiler. Alrighty, so this is our axiomatic system. From those 5 axioms we just discussed and the 3 undefined terms, all of math is derived. So what happens if we allow lines to curve and planes were not flat? So what happens if we deny this 5th postulate and we allow lines to curve? So now, instead of there only being one line that's parallel, that never intersects this line and goes through point C, what if we allow there to be other lines? So what about a line that would look something like this? And pardon my weird drawing, but technically this line does not intersect line AB, and it also goes through point C. If I drew it right, you're just going to have to like roll with it. It's easier to draw whenever I'm on the smartboard in class. Can I fix that one? Whatever. OCD is getting on me. All right, so let's assume that there was more than one line, and that essentially lines are allowed to curve. They don't have to be straight. And planes are allowed to curve as well. They don't have to be flat. Well, what would the world look like if we denied the fifth parallel postulate? Our architecture might look a little bit different. Now lines are no longer straight. You got all this curvature going everywhere. Up is down, down is up. You're kind of discombobulated. Also, the planes and the flat surfaces are no longer flat. They're curved. And this is crazy. I don't want to live in a world like that, but oh wait, we do. The ocean is not flat, right? Spoiler alert, the world is round. Sorry to all you flat earthers out there to deflate your flat earth bubble. But satellites' orbits as well are curved. They don't travel in straight lines. So there is actually use for non-Euclidean geometry. And there are times when we want to look at lines that are curving and that are not necessarily flat planes as well. Given the example. So there are times when we deny the parallel postulate, essentially, and we have this totally different geometry, which is called non-Euclidean geometry. And it is really, really dope. How you say so? Well, let me show you spherical geometry. First thing you need to know about all spherical geometry is a sphere, which is a perfectly round surface, right? It has two different kinds of circles or intersections that we can cut. One of them is called the great circle. The great circle is the largest possible circle that you can have on a sphere. Then you have something called the small circles, which are other intersections that are obviously smaller. Now, how do you get the great circle? So a great circle is unique from a small circle because it cuts a sphere exactly in half. And if you're wondering this video is going a little bit long, I'll go ahead and tell you now, you don't have an assignment, so all you have to do is watch the video and enjoy. So with spherical geometry here, what's interesting is that let's say we have 2 points on a sphere, like location P and location Q, or point P and point Q. The shortest distance between those 2 points is always going to follow a great circle circumference, the largest circle that we can cut it in. And so this circle here is going to be the path that we would follow if we just went straight and we kept going straight without turning. It would be the shortest distance between P and Q, and it would be a great circle path and not a small circle path. So that's really significant because we use that in navigation all the time, trying to go from point A to point B. And if you're flying in an airplane and you're showing a two-dimensional map and you're flying, let's say, to Los Angeles, it'll look like you're actually curving up, but you're actually not curving at all. You're going in a straight in the shortest distance that is possible because the Earth is round. I know. You still don't believe me. Don't worry, I got another slide. I'll prove it to you. So how do you find the great circle circumference? Well, the best way to do it is imagine that you have an orange and you have 2 points that you're putting on that orange and you want to cut that orange in half. There are lots of circles that you can cut that orange and slice that orange in, but you're looking for the one that would go through those 2 points, P and Q, and would also cut the orange exactly in half. Can you picture it? Good. You're visualizing geometry. This is really good. All right. Now, any way that we could cut that orange that would be exactly in half would be a great circle circumference, like the equator and the prime meridian. What's also interesting about any great circle circumference path is it will always cross the equator exactly twice. Can you picture that? It'll also always cross the prime meridian, which is the one that goes north and south, right? It'll always cross that twice as well. Regardless of any way we cut this orange in half, exactly in half, with a great circle circumference, it'll always intersect the equator and the prime meridian exactly twice, which is really cool. Isn't it fun? Oh, that should be a different color. Sorry. It matters to me. All right. So, yeah, great circle, just like the equator. All right, proof the Earth is round. I know, there's so much I'm packing into this one video. All right, proof the Earth is round. So let's say that we traveled a certain distance, like a quarter of the Earth or whatever, and then we going in a straight circle, which is a great circle circumference, just like following along the equator. That would be the shortest distance traveling from point A to point B along the equator, and then we do a right turn. Okay, and then we travel the exact same distance we did following another great circle circumference, a straight path on a curved surface. All right, and then we do another right turn here and we travel the exact same distance. So we just created an equilateral triangle, right? And what's interesting is if we do that and it's a certain distance, I think it's 25% of the Earth's radius or circumference. I could be wrong on that. I actually haven't looked it up, but you know, it's kind of cool. Then we will end up right back where we started. You can actually like do this. If you get on an airplane, go a certain distance, take a right turn, go straight a certain distance, or right turn, go straight that certain distance again, you'll wind up right back where you started. I wish we could do this, but the Earth is too big. So if the Earth was flat, what would happen? If we go a certain distance, a right turn, the exact same circle distance, the right turn again, and the exact same circle distance again, where would we end up? Not where we started. We would have to do another right turn and do the fourth side of our square. Okay, but because the Earth is round, this actually works. So if the pictures from space didn't convince you, then maybe this would. Also, you probably should stay away from Tide Pods. Okay, inside jokes. All right, so there are three different types of geometries that we have. We have Euclidean, which is where lines are straight and planes are flat. That's what we're going to be working with pretty much the entire year. Maybe towards the end of the year, I'll bring out the elliptical or spherical geometry again because it's pretty dope. And then we have hyperbolic and elliptical. So elliptical is kind of when the planes are curving outwards, okay, and then kind of like a sphere, right? And hyperbolic is when the planes kind of curve inside, like a monkey's saddle, which is actually what we call that, or similar to a monkey's saddle, which is really cool. So what happens in these three different types of geometry, these two are also both called non-Euclidean, that's Euclidean, is with our parallel lines. So let's say we have a line here on a flat surface, and we have a point up here, and we draw another line. It's going to be parallel, and there's only going to exist one. Oh, sweet. Forgot I did that. There's only going to exist one unique parallel line that goes through this point C. But what happens if we try that on a hyperbolic surface? So if I try drawing that line, the lines are now curving outwards and away from point C, which would look something along the lines of this. So there's not just one line that will never intersect AB down here that goes through point C. There's actually technically going to be infinitely many of these lines that will go through it. What? There's infinitely many parallels, and on this one there was only one? All right, so that was not a 1. Now it's a 1. So there's one parallel here, infinitely many parallels on this one. So then what are we left with? I think 3 erases, 4 erases. Boom. Who needs a smart board? A digital writing tablet. All right, so what happens in spherical geometry? Well, now things are curving down and in like a great circle circumference. Every great circle circumference is going to intersect this equator. Okay, so let's call the bottom line the equator. We pick any point here and we travel in any direction. That shortest distance will always curve down and end up intersecting those lines. The artwork is struggling here. Sorry, guys. But it's always going to curve down. So there are actually no parallel lines on a sphere, which is crazy, meaning in any direction that you take off in, you will always intersect the equator twice. And if we let this original line be the equator, that's pretty well how it works. So it doesn't matter that we're starting in the same place. No matter what direction we go in, we cannot form a parallel line because we will always intersect the equator. And if we were trying to go in a path that would not intersect, right, then that's not actually a straight line anymore because it's not a great circle circumference, just like we have here, Q, right? If we went a path on the top, that's not the shortest distance from P to Q. It will always cross here. So anyway, that is it. Just under 40 minutes. I hope you guys followed through the whole thing. Lots of really cool stuff. And if I'm honest, some of this I didn't even learn about geometry till I got to college. So I wanted to share it with you. Again, the whole course is not going to be this like mind-blowingly awesome, but it will be. And we're definitely going to go slower, and we're going to take these concepts kind of one step at a time, and eventually you'll get to the point where you can process all this geometry that I got into here. But hopefully you can see my enthusiasm for the subject. I think this is way cooler than algebra. It is super awesome, and what we can do with straight edges and compasses and constructions and protractors. I think you guys are going to really enjoy this class, and I'm really looking forward to when we get back together in person. But until then, I'm going to try to make the best videos. They will definitely be shorter than this one because I know you'll have assignments starting on Monday. So we'll start all of our unit and our vocab on Monday, and I'll go easy on you guys, and because I know you just got out from 4 months of like brain dead, soaking up as much Netflix as you possibly can. So I'll go easy on you guys, and you're going to make it. All of my students last year, they all really did really well. If you talk to any of them, they'll tell you about this class, and you'll really only hear good things. And so I'm excited that you guys are here. It's no mistake that you're here. If you either chose me or I chose you, either way, you guys are the best students that we got at Putnam City High School, and you deserve to have the best math education. And so I'm looking forward to, of course, I hope you guys have a good weekend. I'm looking forward to starting the unit on Monday.